All right, welcome ladies and gentlemen. This is the video on types of intermolecular forces of attraction. The goal is that after watching this video, you will be able to correctly identify the different types of IMFs and to use the compound of an element the formula of a compound in order to identify the types of intermolecular forces of attraction that are present. So we're going through our different types of IMFs, and the first type is called an ion dipole force. Now, this is a fantastic name for the IMF because it tells you exactly what is involved in this attraction. As the name says, it's between an ion and a polar molecule. So exactly as you would expect, because remember, dipole means polar. And the force of attraction is due to the fact that the ion has a charge. So in this example with the sodium, right, the sodium has a +1 charge, and this is your polar molecule, which has the two different sides. So this is your partial negative, and this is your partial positive. Remember, these aren't whole charges, but there's going to be an attraction between the positive ion and the partial negative side of the polar molecule. You notice that the polar molecule has lined up accordingly. Likewise, if we take iodide ion, for example, we have a negative charge there, and now our partial positive charge on the dipole is lining up to interact with the negative ion. So this is a force of attraction. This is not a bond, but this is a fairly significant force of attraction. This is a fairly strong IMF because it does involve a whole charged particle. Now, Coulombic attraction has a big impact on ion dipole forces. We see here in this example we have water, and you'll notice that the water is oriented. The oxygen side is facing both of these ions because both of these ions are positive. So the partial negative side is oriented towards it and the partial positive is oriented away from it. But we have sodium here, which is a charge of +1, and magnesium here, which is a charge of +2. Because the sodium has a smaller charge, while there definitely is an interaction between the sodium and the water, it is going to be a weaker interaction than that between the magnesium and the water. The magnesium will have a stronger ion dipole force with water. Moreover, because the radius of sodium is larger versus the magnesium ion, which is smaller, all of this points to this being a stronger interaction. Again, Coulombic forces, the magnesium ion is smaller, so it can get closer to the water molecule, and the sodium ion having a weaker ion dipole force with water. The next type of IMF is called dipole-dipole forces. And again, dipole means polar. So now we're moving away from the types that involve charged particles to those that involve neutral particles. So polar molecules, because they have two different sides, the opposite ends of the dipoles will attract one another. There is going to be an attraction between the partial negative in one polar molecule and the partial positive in another polar molecule. Molecule 1, right? Partial negative, partial positive. Molecule 2, partial negative, partial positive, and in between right there, that's your dipole-dipole force. That's your dipole-dipole force of attraction. Now, the strength of the dipole-dipole force can alter from compound to compound. The more polar your molecule is, the greater the difference in electronegativity in your bonds, the more asymmetrical, the stronger your dipole-dipole force is. Likewise, we see an impact with distance. We see that if your molecules are larger, that they're going to have a weaker dipole-dipole force than for molecules that are smaller. And again, this is a type of IMF that is only exhibited by polar molecules. The molecule must have a dipole in order to exhibit dipole-dipole forces. This picture is showing a whole bunch of polar molecules, and you'll notice that we have both attraction and repulsion forces at play here in between the molecules now rather than inside the molecule. But the way that they're oriented is such that they're going to maximize attraction and minimize repulsion. So while yes, if we have polar molecules, we can definitely have the possibility of the partial negative on one being next to the partial negative on another. But in general, you know this, the partial negative, partial positive is sort of oriented this way. We have partial negative, partial positive, partial negative, partial positive, partial negative, partial positive. Basically, we're orienting in order to really try to maximize the attraction that's occurring here. The next type of IMF is called the hydrogen bond. Which, as I've already talked about, is if it's not the worst name in all of chemistry, then it's definitely the worst name in all of chemistry, because this is not a bond. This is a horrible name for an IMF. It is not a bond. Hydrogen bond is not a bond, and I need to be very, very clear about that. It is not a super strong intramolecular force of attraction. It is a compared to the strength of a bond, a hydrogen bond is significantly weaker. But what is it? If it is an IMF and it has this god-awful name, what is a hydrogen bond? It's a super strong dipole-dipole force of attraction. So it's really, think of it exactly the same way as you did dipole-dipole, meaning partial negative on one molecule is attracted to the partial positive on the other, but it's like super strong. I think I compare this to extra strength Tylenol versus regular strength Tylenol, where a dipole-dipole force would be regular strength Tylenol, hydrogen bonding would be extra strength Tylenol, meaning they're both Tylenol, but one is stronger than the other. And it's super strong. It only happens in certain situations. Your hydrogen has to be bonded to an FO or N. So the H has to be bonded, actually bonded to a fluorine, oxygen, and nitrogen. And then it has to come into contact with another fluorine, oxygen, or nitrogen on another compound. This example shown here with water. Water is polar, and water exhibits hydrogen bonding. So you'll notice that we have, this is our H that is bonded to an FO or N, so that's that hydrogen, and it's coming into contact with another FO or N, so it's that one right there, and that interaction between them, where you have the partial positive hydrogen coming close to the partial negative oxygen, that is the hydrogen bond. That's that IMF. Why FO and N? Two reasons. Number one, these are very highly electronegative atoms, so when they're paired with hydrogen, you will have a very large difference in electronegativity. And number two, they're very small atoms. Chlorine cannot participate in hydrogen bonding because it's simply too large. It has an additional electron shell. So because they're very electronegative and because they're very small, we can get this super strong dipole-dipole force of attraction. Now, this is the strongest neutral type of IMF, meaning it's not stronger than ion dipole, but it is stronger than dipole-dipole. So this is all of the types of IMFs that do not involve charged particles, hydrogen bonding will be our strongest. Why is hydrogen bonding considered a special dipole-dipole force of attraction? Basically, why do we have a separate name if it's the exact same thing that's happening, meaning partial negatives being attracted to a partial positive? Because we have graphs that look like this. This is a graph of compounds with hydrogen with different elements in the middle, and it's simply graphing period numbers. So we are increasing by molecular weight versus boiling point. And in general, we have this really pretty straightforward trend of as our compounds are getting larger, the boiling point is increasing, and it's very linear and it's really pretty clear. Except for these three guys. Which are the lightest and the smallest out of all of our options, and yet they have higher boiling points, and they're massively not fitting the trend at all. They are not working at all. They are not fitting in at all. So essentially something else was needed in order to explain what's happening here, because clearly what is happening with water, HF and NH3, is not the same thing that's happening with everything else. They are not fitting the trend. We cannot use the same behavior to explain the phenomenon. We had to come up with something else and say, okay, look, yes, they still might be polar, but this is clearly a very special type of dipole-dipole force of attraction. Need to be very clear about hydrogen bonding. Not every hydrogen can participate in hydrogen bonding. The hydrogen has to essentially fit certain conditions. So your hydrogen can only participate in hydrogen bonding if it is bonded to an FO or N. So the hydrogen itself must be bonded to an FO or N. But that's actually not enough, because then that hydrogen must then come into contact with another FO or N. Essentially, your hydrogen has to be surrounded on both sides by a fluorine, oxygen, or nitrogen. I say FO and NB, I like to say hydrogen bonding is FON. That's kind of the way to remember it. Hydrogen bonding is FON, FON. So as it sort of has this example right here, this would be the hydrogen bond and this would be the hydrogen bond, but you'll notice in both cases, again, the hydrogen is bonded to an FO or N, and then it's coming into contact with an FO or N. It doesn't have to be the same on both sides, meaning as it shows right here, your hydrogen could be bonded to like an F and then it could come into contact with an O, and that would work. That would give you an example of hydrogen bonding. All of these pictures in this chart are showing you examples of hydrogen bonding. Those are the dotted lines. Now, drawing hydrogen bonding, diagramming hydrogen bonding, a hydrogen bond actually forms in a very specific space, so it's not like it's not a random interaction. And you can only get one hydrogen bond forming between one lone pair on an FO or N and one hydrogen atom. This means that there's a limit. There's not an infinite number of hydrogen bonds that a compound can form. So we have a water molecule here on the left and on the right, and you'll notice that here's our H that's bonded to an O, and then it's coming into contact with another oxygen, but the hydrogen bond is actually between the lone pair on this oxygen that's on the right and then the hydrogen that's on the left. So each hydrogen can only make one hydrogen bond, so that's it. That hydrogen is done. That's the only intermolecular force of attraction, only hydrogen bond that H can form. A question that the AP likes to ask is asking you to actually diagram the hydrogen bonding, meaning draw it, meaning draw the locations of the hydrogen bonds. And here's where we're going to use that lone pair idea. So diagram the hydrogen bonding between at least 2 molecules of water and a molecule of an aldehyde. So the aldehyde is shown here. R just means essentially the rest of the molecule. So we're not going to concern ourselves with that molecule. And we have to sort of think, how is the water going to hydrogen bond with this particular compound? This hydrogen will not participate in hydrogen bonding because look at what it's bonded to. It's not bonded to an FO or N, so you do not want to draw your hydrogen bond with that H, which leaves then the oxygen. The oxygen is what's going to participate in hydrogen bonding. So we want water molecules, and because we know it's going to be the lone pairs on this oxygen that are going to be significant, we know that the hydrogen of water must be oriented towards the lone pair. So I'll just sort of draw the rest of the water molecule. And this right here is going to be your hydrogen bond between an H that's bonded to an O that's coming into contact with another FO or N. So, but the question asks for 2 molecules of water. So I'm going to use the other lone pair on this oxygen. I'm going to do the same thing. I'm going to draw an H that's oriented relatively close to the lone pair and then sort of sketch in the rest of the water molecule and then draw in the hydrogen bonds. So we have it here and here. The last type of intermolecular force of attraction is called London dispersion forces, also known as van der Waals forces, but I'm going to refer to them as London dispersion forces and use the abbreviation LDFs. The nice thing is the AP actually tends to use London dispersion forces as well. And London dispersion forces are based on the idea that electrons in a compound, any atom, any species, will not be evenly distributed at every single instant in time because electrons are constantly moving. So there's a possibility to form what is called an instantaneous dipole. If your electrons are not evenly distributed at every moment in time, it's possible to have a dipole, something with 2 poles, essentially polar, that pops up out of nowhere simply based on the movement of the electrons, meaning the electron cloud spontaneously rearranges to create a dipole. Now, the thing is, once this happens in one molecule, it essentially sets off a chain reaction where if one molecule spontaneously turns into a dipole, that will then cause a shift in the electron cloud in the surrounding molecules, causing them to become dipoles, which then we call that an induced dipole, which will then have a series of attractions because suddenly you have these dipoles that are popping up. Well, they're going to be attracted to one another because now you do have these partial negative, partial positive charges. showing a diagram of this idea behind London dispersion forces. On the left, we have essentially a map of electron density. So all the little dots are probable locations for electrons. And you'll notice that looking here that they're fairly well distributed. And this is showing the same picture. It's just sort of showing it with shading rather than dots. So we have no polarization occurring here. So no London dispersion forces, no instantaneous dipole. But then what happens here is we have a shift in the electrons in atom A. And you'll notice that they're sort of all oriented on the left side. So we have the left side being slightly negative and the right side being slightly positive. And it's showing it here again with the shading. Instantaneous dipole on atom A. Well, this is going to set off an effect because atom B next to it is not going to ignore this fact. Suddenly you've had a partial positive charge on the right side of the molecule. So now we get an induced dipole on atom B. And what we wind up with is a partial positive that's next to a partial negative. They are going to be attracted to one another. There's your London dispersion force. Now, the thing about London dispersion forces, what compounds exhibit London dispersion forces? All of them. All of them, because the only requirement needed to exhibit London dispersion forces is that you have electrons. And if you have electrons, then you have the possibility that they're not going to be evenly distributed at every single moment in time. So all compounds, no matter whether they're polar or nonpolar, no matter whether it's an ionic solid or a metallic solid, every single thing that has electrons exhibits London dispersion forces. Of the types of IMFs that do not involve a charged particle, this is actually considered, generally speaking, the weakest because it's very short-lived. This is an instantaneous dipole. It sets off an induced dipole. That dipole will not stick around forever. It's not a permanent dipole. The electrons will eventually start to arrange themselves back into a more symmetrical shape. So it's short. It's very, very short. But the thing is, the more electrons a compound has, the stronger the London dispersion forces become, because the more polarizable, we call it more polarizable, the more polarizable the compound becomes, the more possible it is to have, basically the stronger a partial negative and the stronger the partial positive you can get. So this actually can become a very strong intermolecular force of attraction if you have lots and lots and lots and lots of electrons. So while I would say it's weak, I'd also say there's huge variability in the relative strengths of this particular IMF from compound to compound, and it all comes down to how many electrons the compound has total, not just valence electrons, but all of them total. And you'll see here in this chart, we have a comparison of the noble gases and their freezing point. So this is actually an effect of the London dispersion forces. The stronger the IMFs, or the stronger the London dispersion forces in this case, the higher the freezing point will be. And helium only has 2 electrons versus neon has 10, argon has 18, krypton has 36, and xenon has 54. And you'll notice that xenon here has the highest freezing point. Right, convince yourself that negative 112 is much larger than negative 270 for the helium. So we have actually a big effect that even though all of these atoms only exhibit London dispersion forces, we see actually a very big increase between the freezing point of helium, which has the weakest London dispersion forces out of all of the noble gases, to xenon, which has the strongest in this particular chart. Now, London dispersion forces are also impacted by the shape of the molecule. You could have 2 molecules that have the same number of electrons. Both of these guys are pentane, meaning they have the same amount of electrons. But they're structural isomers of one another, meaning they're arranged differently, so they do have different shapes. The pentane that's on the left here, it's in a straight line, versus the pentane that's on the right, it's more circular, or spherical, I should say. The one that's arranged in a line, because it's flat, the surfaces can line up, and you can have a lot of contact between the 2 molecules, versus the one that's spherical. less surface area. So you can actually have weaker London dispersion forces. Basically, the induced dipole, there's less of a sort of an area for them to form that attachment, and you see the changes in their boiling points. The boiling point of the one that is flatter and has more contact between the molecules is higher than the one that has less surface area. So this flow chart right here is really sort of summing up how you identify what type of intermolecular force of attraction your compound has. The first question you want to ask is, are ions involved? Because if they are, then we're going to be looking at these two possible choices. If it's just ions, meaning there's no polar molecule, so we're looking at that question right here, then we'd say that the force of attraction is ionic bonding, so sodium chloride, ammonium nitrate, etc. But if we have both ions and polar molecules, then we have the ion dipole force. So we have that force of attraction between them. An example of this is any ionic compound dissolved in water, it would exhibit ion dipole forces of attraction. If ions are not involved, then we're going over here. And our next question is, well, if we don't have any charged particles, do we have polar molecules? So if we do have polar molecules, then we have to consider essentially what type of polar molecule is it. If we don't have hydrogen atoms that are bonded to an F, O, or N, meaning we're going down here, then our type of IMF is a dipole-dipole force of attraction. But if we have a polar molecule, and in that polar molecule we have hydrogen atoms that are bonded to an F, O, or N, then we have hydrogen bonding. However, if we ask this question, are polar molecules involved, and the answer is no, meaning everything is nonpolar, then we have London dispersion forces only. And that only is actually important because really for all of those choices, dipole-dipole forces, if something has dipole-dipole forces, it also has London dispersion forces. If you have hydrogen bonding, you also have London dispersion forces. If you have ion dipole forces, you also have London dispersion forces. If you have ionic bonding, you also have London dispersion forces, because everything has London dispersion forces, because everything has electrons. And on the bottom here, I have also indicated that these are organized in terms of increasing strength. So all of these London dispersion forces are the weakest, and ionic bonding is the strongest. And very quickly, just a sample question to finish this up, what types of IMFs exist between each of the following molecules? Realistically, you need to draw that. You need to draw the Lewis structure. There's no way to identify whether or not you have a polar molecule simply by looking at the formula, unless it's one that you memorized. But trust me, the AP will probably give you ones that you have not memorized. So you want to draw the structure in order to think about whether or not it's polar or nonpolar, because that's something that is critical to answering the question of what type of IMF you have. So we have HBr in stage 4. So just drawing those Lewis structures real quick. We see that HBr is asymmetrical, so it's a polar molecule. There are no ions involved here, right? This is not an ionic compound, so I'm more on the left on that flow chart. It's polar. But it doesn't have a hydrogen bonded to an F or N, so that's going to mean it will have dipole-dipole forces. And London dispersion forces. So HBr exhibits two types of intermolecular forces of attraction. And then we look at the CH4. Again, this is not an ionic compound, so I'm not thinking about ionic bonding or ion dipole forces. I look at the structure and I see this is a symmetrical structure, so CH4 is nonpolar. If it's nonpolar, that means that we only have one type of intermolecular force of attraction. So methane exhibits London dispersion forces. So those are our types of IMFs. So be prepared to answer questions where I give you compounds and I ask, hey, what type of IMF is in this compound, or what is the strongest type of IMF that is in this compound?